I want to start by thanking the RSS and the editors and the AE and the referees and the discussants. This is really an honor for me and the other authors of this paper. And now that it's accepted, I feel like I can say this and people will believe me, that the feedback we got was really of very high quality, and it really helped us understand the problem a lot better and I think improve the quality of the paper. So this is joint with people at NC State and also at UNC. It's funded by several different sources: National Science Foundation, National Institutes of Health, and the Department of Natural Resources. And I highlighted, I have all the collaborators there, but I highlighted one, which is Nick Meyer, who's in the back. This is Nick's thesis work, and Nick did all the sort of heavy lifting in this problem. And so I'm really just here taking credit. So the problem that motivated this work was white nose syndrome. And so this is a fungus that affects bats in North America. And it's really devastating to bat populations there. It's killed millions of bats. It's 90% fatal for some species. You go to these hibernacula, and there was millions of bats, and now there's 0 or hundreds. I mean, it's really amazing. And I've pulled some headlines here. You can see that they're not very sunny. So fungus that's killing millions of bats isn't going away. The secret bataclysm, white nose syndrome, and extinction, and relentless bat plague not abating. And so this is something that has been going on since 2006, and it doesn't seem to be slowing down. And so there's enormous impacts both on the environment, but also on farming and agriculture, because these are natural predators of insects. And so as they've been dying off, they've had to replace that insect control with pesticides. So the disease spreads on hibernating bats. And so in the lower left picture there is a bat that has white nose syndrome. So living up to the bat stereotype, it's upside down, and it has some white on its muzzle. So its muzzle's near the bottom. You can see this patch of white. That's this fungus. So the fungus gets on them. When they're hibernating, they don't move, so it just grows on them unchecked. And as it grows on them, it destroys the membranes in their wings, and it kills them. So one of the primary questions was, if we have a subset of interventions, so they were testing these in sort of laboratory settings, where should we put them to control the spread of the disease? And so one of the main interventions is shown here in the middle. That's a schematic for an artificial cave. And it may be hard to see, but there's a little black speck at the bottom of that picture, and that's a person. So these are very big. These are big structures, and they're very expensive. So an optimal thing to do would be to put these all over the place, but they can run as much as $1 million a piece, and so that's just not feasible. So the question is, where should we put them based on what we know about the disease, and then how should we move them as the disease evolves? And then, just as a bit of trivia, on the right, I put up a poster that I saw while getting my oil changed, which tells us that Chevrolet is using Corvette byproducts to make the stalactites inside these artificial caves. And so when I was really thinking about this a lot, it seemed like everywhere I looked was white nose syndrome, even at the oil change place. And one of the big problems is that they haven't made a lot of progress. Well, maybe I shouldn't say that, but there's still a lot left to learn about how the disease spreads. So the outbreak was 2006. This is an article from 2017 in August about whether or not the fungus spreads during the summer and how much it spreads. Okay, so that shows you that there's still a lot of open questions about the disease dynamics, even as recently as August 2017. Okay, so the problem is as follows. So this is a map of the US. Each of these outlined regions is a county that has caves that are known to house hibernating bats that are susceptible to white nose syndrome. Okay. So every point in time, you go out and you measure certain attributes of these counties, which include number of caves, species richness, average winter temperature, which is important for this problem because it's a cold-loving fungus, and so on. You also, of course, know where the disease is spread. And so you take all that information together, and you want to choose a subset of these locations at which to apply a treatment. So you can think about artificial caves for the purpose of this talk. And then you put the caves down, you go forward a year, and you remeasure everything. And then you're allowed to change where those interventions are or keep them where they are. And the goal is to do this in such a way to control the spread of the disease over a long time horizon. Okay. So placing these interventions is going to serve two purposes. One, control the spread of the disease, but also it's going to help you learn about the effectiveness of the intervention and the dynamics of the disease. So you need to do two things at once. That's estimate the intervention effectiveness and the dynamics of the disease, and then of course also try to control the spread of the disease. So formally, we'll be looking at what's called an allocation strategy, and this is a map from current epidemic status to a subset of counties marked as high priority for treatment. There's a lot of problems that have the same form. So the most obvious one is a disease spreading on a human network. So you have network where the nodes are the people and the links are some kind of social connection, and you have the disease spreading across that network. There's also problems like this in ecological management. So for example, managing catch sizes, if you're talking about, say, fishing, or hunting licenses, if you're talking about game birds and so on. And something that's really big in North Carolina is something called precision agriculture. So in Stat 101, we like to talk about having 3 plots of land and 3 different fertilizers, and we put them on there and we estimate the mean yield. Well, now they think about how to adaptively place the fertilizer down to the square inch, right? And so it's really kind of incredible. So that's another kind of emerging area for this type of methodology, and there's lots of others. Anything with a spatial temporal feel. Okay. So why we thought this was an interesting problem, and also why I was so excited to have people discussing it and to get some other perspectives on this problem, is that it's a difficult one. So in terms of the data, when you start, you have no information about the effectiveness of these interventions. So they may have been tested in a lab, but you don't know how they're going to work out in the field. And so that means you have to learn as you go. The data themselves are noisy, incomplete, and sparse. So in the bat case, people are going out into these caves and looking to see if the disease is there and counting the number of bats that have infections. So it's obviously prone to measurement error. It's prone to convenience sampling. They're not going out there at the same time every year. They're not even going each place every year. I'll completely ignore this for the rest of the talk until the very end. It's high dimensional. So in white nose, you have about 11,000 measurements per time point you can use to inform your decisions. In terms of estimation and inference, from a statistical point of view, this is a complicated problem because at every time point, you use the data you have to inform the allocations you choose. Okay? And so everything is dependent on the past data, and so you have this constantly changing distribution of allocations, and so you end up with a process that may not even be stationary. Okay? So that makes things like confidence regions and prediction regions complicated. Computationally, if you have allocations and you can do something or not do something at each one, there's 2 to the L possible allocations or interventions, and that's at one time point. Okay, so if L is 1,000, you have 2 to the 1,000 choices, right? So that's more than you can enumerate, on a supercomputer, and we're talking about not just one decision, but many into the future. Okay, so there needs to be some way to control the size of that search space or the size of the allocation space. Okay, so here's an outline to the rest of the talk. First, I want to define what we mean by an optimal allocation strategy formally in terms of potential outcomes. That was one of the first steps in this paper, was just trying to get our act together in terms of defining what we mean, especially because this is a spatial problem. There's spillover effects, and trying to account for that. Then I'll talk about estimation with a parametric dynamics model. Just as fair warning, there's 2 slides in there that kind of go beyond what's in the paper, trying to establish some of the properties of the estimator that's proposed in the paper. And then I'll show some simulation experiments and talk about some open problems. Okay, so we'll think about an allocation problem that's evolving over allocations, and we'll number those 1 through capital L. So these could be the counties in the white nose problem, or they could be nodes in a network or something else. And we'll think about a process that's evolving in discrete time, labeled 1, 2, and so on. In white nose, these are fixed time points, in calendar time, once per year. But in other problems, they may be event-driven. So something happens and you make a decision. And so we're just thinking about those as happening in discrete time. At every time t in every location L, you observe a state, which we'll call SLT, that takes values in RP. You observe an outcome, YLT, which is scalar valued. You select an allocation, ALT, which we'll code as 0 and 1. 0 means you don't do anything, and 1 means you do something. In our case, you may think about that as putting a cave there or not. And then we'll omit a subscript to denote the union over all locations. So ST with no subscript would be the set of all states at time t across the locations, 1 through capital L. AT would be a vector of length capital L of 0s and 1s, encoding which ones got treatment and which ones didn't. And then YT would be this vector of length L of outcomes. Okay, and we're going to assume that the allocation is based on the state ST at time t. What that means is that we've defined the state in such a way that it's not just things that were measured at time t, but it's a summary of everything that's happened until time t. So it includes all the salient features we need to make a decision. Okay, so we need to learn as we go. And one way to do that is through random allocations. And so what I mean by that is, given the data you've seen so far, the allocation you choose is still stochastic. So it can't be a deterministic function of the data up to that point. Okay? That's necessary to identify the optimal treatment strategy. So if you think about something like adaptive clinical trials, it's a similar kind of approach where, given all the patients you've seen so far, your probabilities may depend on, your randomization probabilities may depend on past patients, but they're not deterministic. So formally, let B sub L denote the set of all distributions over binary vectors of length L. Those are your allocations. And S be the domain of the state. Then an allocation strategy pi takes as input a state and gives as output a distribution over allocations. Okay? So under pi, a decision maker who observes state st equals little st will select allocation at with probability pi of at st. Okay, so the idea is you get a state, and then out of pi comes a distribution over possible allocations, and what you'd like is for that distribution to become increasingly concentrated on the optimal strategy. So we're going to focus on estimation within a predefined class I'll call capital Pi. And the reason to do that is because it allows us to enforce constraints. So in the white nose problem, we can only treat a small subset of the locations, and so this class will encode those constraints by only putting support on allocations that say treat at most, say, k locations, if k is the constraint. There are other reasons to do this. You might think about classes that are interpretable or parsimonious, or maybe computationally scalable, and so on. The particular class of policies we'll consider is a mixture over a deterministic class. So these are stochastic policies of the form pi of as is the integral over a class of deterministic functions, meaning they take as input a state, they give as output an allocation. Okay, so it's a mapping from states to allocations. And so it's the integral that the deterministic policy E at S would choose A, and you integrate it against this mixture distribution P. Okay? There's two reasons to do this. One is if you're trying to come up with a class of stochastic strategies, it's very difficult. You're talking about stochastic process that takes values in binary vectors of length L, right? But you can talk to a domain expert about what would you do in this state? What allocation would you choose for a given state, or what form might a deterministic treatment assignment rule look like? Okay? And so you can get that. That'll be this class delta. And then you mix over it to get a stochastic class. And the other reason is going to come out later, which is thinking about what the optimal mixing strategy is. And it's going to turn out that the sort of optimal choice for P at time t is going to be the posterior probability that E is optimal given the data you've seen. Okay? So that's going to end up being kind of the punchline at the end of this. Okay, so just to make things concrete, this is an example of a deterministic class. This is what we'll call a priority-based class. So the idea here is simple. You take every location, and at every location you're going to compute a score. And then you're going to rank them by their scores from highest to lowest, and you'll treat them from highest score to lowest score until you run out of resources. Okay? And that score, the way I've written it here, is going to be a linear function of some features. So at every location you construct a vector of features, and that may include things like features of that location. It may include its susceptibility to becoming infected. It may include the probability it will create secondary infections if it becomes infected. It may include properties of its neighbors and so on. Okay? So it can be arbitrarily dependent on any number of models for the spread of the disease and so on. But it's some feature vector you compute at each place. And then there's a weight vector, which I denoted as kind of script rho, that's used to combine the features into a final score. Okay? So given the features, every choice of rho gives you a different priority scoring, and if we rank them and then treat from highest to lowest, that gives us a different deterministic policy. Okay? So given rho, you have a ranking function. Given the ranking function, you know which ones you're going to treat, and so rho indexes a class of deterministic rules. And the thing is, you can talk to domain experts about what those features should be. So that's the idea. Okay, so these features can account for local information, predicted treatment effect, and so on. And if we treat the highest priority locations until our resources are exhausted, then that gives us a class of deterministic maps. And the nice thing here is that when we optimize over those maps, as we'll do later, you can optimize over those weight functions, which live in RD. So you're optimizing over Euclidean space, which is generally easier than optimizing over a general class of functions. Okay? Of course, the methodology isn't restricted to deterministic classes of this form, but this is maybe something to keep in mind, and this is what we'll do in the simulations. Okay, so to formalize an optimal strategy, we use potential outcomes. So we use an overbar to denote history. So A bar T would be A1 through AT, and then W star is a set of all potential outcomes. So that includes Y star T of A bar T, So that's the outcome you would observe at time t if you used allocation sequence a bar t. S star of t plus 1 of a bar t is the potential state you'd observe at time t plus 1 under treatment sequence or allocation sequence a bar t. And that's over all sequences a bar t over all time points. Okay, so that's the whole collection. And then a potential outcome under pi has this sort of horrible expression, but the thing to remember is that y star t of pi is the outcome you would observe if you were following pi. That is, you were choosing allocations based on pi at every time point. So mathematically, what you do is you take a sum over all allocations, you take the potential outcome under that sequence of allocations, and you multiply it by a product of indicators that picks off the allocations that would have been recommended by pi. So formally, you define this set of random variables xc pi t of s that's indexed by both t and s, and they satisfy the probability that xc v pi of sv equals av is the same as the probability that it would have been chosen under pi. So it's just a way of mathematically writing down the fact that you have a stochastic policy that's picking off the sequence of allocations, and y star t of pi is the outcome you would get if you were following pi. Okay, so that expression won't show up again, but it did take us some time to think about how to formalize that. Okay, so we'll define optimality in terms of the discounted marginal mean outcome under pi. So define v pi, the expectation of the sum over time of gamma to the t minus 1 times u of y star t of pi. So here gamma is a value between 0 and 1. Okay, so it's decaying exponentially as t increases. And then u is some utility function. So it takes as input this entire vector of outcomes, y, and it gives you back a scalar. So in the disease case, it could be a sum of all the infected locations, so just how many are infected. It could be that sum weighted by the number of caves in that location. It could be that sum weighted by the number of bats estimated in that location, and so on. Or it could be a measure of cost, etc. And so the optimal strategy, say pi opt, gives you a marginal mean outcome that's at least as big as any other pi, where pi and pi opt are both in capital pi. Okay, so whenever we talk about the optimum, we mean optimum within the class you're considering. Because in a lot of cases, the optimal is going to be just treat everything all the time, right? So we're interested in the best you can do given the constraints that you have. Okay, so in order to connect that definition of optimality with the underlying generative model, we're going to make the following assumptions. So let ht be the information you have at time t to choose an allocation. So it would be all the states up until time t, the allocations up until the previous time point, because you're going to choose at, and the set of outcomes up to the previous time point. And then the sort of usual causal inference assumptions for sequential decision making are as follows. Sequential ignorability. So the allocation choice at time t is independent of the potential outcomes given the history. So there's no unmeasured confounders. This is sort of the sequential analog of that. Consistency. So yt is y star t of a bar t, meaning it's the potential outcome to the allocation sequence actually chosen, and then st is s star t of a bar t minus 1, so the observed state at time t is the potential state under the allocation sequence actually given. And positivity, there exists some epsilon such that the probability of choosing allocation little at given the history is at least epsilon for what I'll call all pi feasible at. What I mean by pi feasible there is those little ats can only be set to values that are allowable under the class you're considering. You don't have support on allocations that you're not allowed to choose given the constraints that are inherent in capital pi. Okay? So you can formalize that, but that's the idea. So in sort of dynamic treat regimes and other sequential decision problems, usually the next thing to come is sutva, right? But that doesn't happen here, it doesn't hold here. And the reason is that there's interference, meaning that if you apply treatment in one location, it can affect the outcomes at nearby locations. Okay? So this happens, and in fact, you hope this happens, right? So you hope to have an effect on nearby locations. So the spillover effects, because of this sort of spatial dimension, they violate SITFA, and without any additional assumptions, the experimental unit would be the collection of all the locations. So without any assumptions about how or the degree of the spillover effect, you can make no gains, and you have to say, well, the set of locations is the experimental unit. Okay? So there's no pooling. Even still, it's possible to identify the expected utility, to write down the expected utility in terms of the generative model. So under those assumptions, the expected utility at time t under pi can be written as follows. It's the integral of the utility times this product of density. So it's the density at time v of the outcome at time v given the history and allocation. There's your policy pi. There's the conditional density of the history time v given the previous history, and then some dominating measure. And so if you look at this, these are all in terms of the data generating model. Okay? But the problem is that if we have one observation per time point, we can't identify any of those densities, right? You can't identify the conditional density of the history at time v given the previous history. You only have one history at time v, right? And same thing for the outcome. So the natural thing to do is say, well, what if we assume it's somehow homogeneous? So we'll get rid of that subscript. So we'll say that the distribution of the history doesn't depend on v, and the distribution of the outcome doesn't depend on v. Even still, if you thought about non-parametric estimation, it's practically impossible because you're conditioning on a categorical variable that takes values, on the order 2 to the L, right? So the amount of data you would need to estimate these things is enormous. So from any sort of practical point of view, and this is probably obvious at the onset, you need to pool over locations somehow. So they're not independent, but you need to be able to pool across them or the problem's hopeless. And so one way to do that is to model the treatment effect, and so that's what we're going to end up doing. Okay, and so that leads us to estimation with a parametric model. So we're going to assume that we have a Markov model for the system dynamics. So we'll specify a conditional density for the outcome. So the density that we had, which was FV, YV, given the history, and the allocation, isn't going to depend on time, and it's only going to depend on the current state and allocation, and it'll be indexed by some parameter beta. Here we'll assume that beta is finite dimensional and fixed. You could generalize this by putting a state space model in for beta or having a sieve that grew in dimension and so on, but we'll assume that it's fixed. And we also are going to need a conditional density for the state because the outcome depends only on the state. So we'll assume that the distribution of the state depends only on the previous state and allocation. It doesn't depend on time, and it's indexed by a parameter theta. Okay, so now there's two parameters here, beta and theta, that determine the entire system dynamics. So if you know beta and theta, you know everything about this process, and then it just becomes a matter of using the dynamics to solve for what the optimal strategy is. Okay? So the idea is sort of stated algorithmically here, which we call simulation optimization to estimate pi-opt. First, you construct estimators beta hat and theta hat of beta and theta. Okay, so we'll do this using maximum likelihood. And then you draw beta tilde and theta tilde from the sampling distribution of beta hat and theta hat. And I'll talk more about why we do that in the next slide. Then you assume that beta tilde and theta tilde are the true parameters. And if you assume those are the true parameters, you know everything about the disease dynamics. So you can simulate to construct an estimator v hat of v. Remember, v is the marginal mean outcome, and you can plug in any strategy there. And you use stochastic programming to compute e hat to be the argmax over all deterministic classes of v hat of e. So that is, you find the deterministic strategy that maximizes the estimated marginal mean outcome. So it's easier to see in a picture. So this is the schematic. So you start off by observing state S. You do maximum likelihood. That gives you beta hat, theta hat. You sample beta tilde and theta tilde from their sampling distribution. You plug those in to get an estimator v hat. You simulation optimization to get the maximizer over your deterministic class e hat. Set A to be e hat of S, and that just goes round and round. Okay? So every time point you go through this loop once. And so what's happening here is that we're really using the sampling distribution of the MLE as a surrogate for a posterior. And if you think about beta tilde and theta tilde as being a draw from a posterior, then that step plus the next step is really drawing e hat such that the e hat you get is proportional to the estimated posterior probability that it's optimal. And this is just a version of Thompson sampling. So Thompson sampling is an old idea. So it was published in Biometrica in 1933 in the context of treating patients. So the idea was patients would arrive, and with every new patient, you computed the posterior probability that each of their treatment choices was optimal, and you sampled treatments proportional to those probabilities. And the same thing is happening here, only now the analog of the treatments are these deterministic policies E. And in place of a posterior, we've used the sampling distribution of the maximum likelihood because MCMC is expensive in this context. Okay, so I am going to go off book here for a second, or off paper for a second. So I have two slides that aren't in the paper, but this paper was originally submitted in 2015, so we've been thinking about this a lot since then. And so I thought we might want to say something about the properties of this estimator. So it's highly algorithmic, as you saw in the picture. So what can we say theoretically? So I won't go into the technical assumptions. I just want to give a flavor. So we're going to assume the parametric model is correctly specified. So without that, it's hard to say what the estimator is doing. We'll assume that pi-opt is in the strategy space pi, which either means the true optimum is in pi, or more likely the thing you're interested in, you're calling pi opt is in that class, the best you can do in the class you're considering. We'll assume the parameter space is compact, the likelihood is smooth, and we're also going to need some equicontinuity conditions, sort of in the spirit of Hyman and Magnus. I should say that even though you do maximum likelihood, everything is dependent here, right? So you have to use some of this data, this maximum likelihood theory for dependent data rather than sort of standard maximum likelihood theory. So there is a little bit more work that needs to be done to get that sampling distribution. But under these conditions, and those and the causal conditions we made earlier, if we let pi hat be the Thompson sampling estimator at time t, and we assume A1 through A5, and A to t is any sequence that diverges to infinity, that satisfies A to t equals little ot, then you can show that the marginal mean outcome under Thompson sampling minus the marginal mean outcome under the optimal is big OP of square root A to t over t plus gamma to the A to t. So if you minimize this over A to t, this holds for any A to t, but if you minimize it over A to t, you end up with something that gives you an order of square root of log t over t, which shows up in some problems as being a rate that you can improve on. One other interesting thing about this theorem is that, well, A to t can be chosen arbitrarily, provided it satisfies these conditions. It turns out that in the proof, A to t is how far into the future you simulate when you're constructing v hat. So remember, you get a beta tilde and theta tilde, and you estimate the marginal mean outcome, assuming those are the true parameters. When doing that, you have to simulate into the future, and you can't go infinitely far in the future. So A to t is how far you go. And what you see here is that the first term increases as A to t increases, but the second term decreases as A to t increases. What this says is you can go too far, right? So even if you had infinite computing resources, it would not be optimal to go as far into the future as you could. And that makes sense because if you have the true parameters, of course you should go out as far as you can, right? And the farther out you go, the better you're able to approximate v for the parameter estimates you have. But because of the incorrect estimates, the farther out in the future you go, the bigger the extrapolation error becomes. So there's this trade-off. Okay? And so this actually gives you some guidance about how to choose how far you should simulate in practice. Something about the finite sample properties, and this is the last non-paper slide, and I realize it's maybe the most horrible looking. But I wanted to say something about the finite sample properties. So we're going to define pi beta theta opt. So I'm making the dependence on the parameters explicit just so it's easier to follow. To be the argmax of the marginal mean outcome over your class if beta and theta were the true parameter values. Right? And define r beta star theta star epsilon to be the worst you could do in terms of performance if you picked a parameter value in an epsilon neighborhood of the truth. So the truth are beta star theta star, and you were in an epsilon neighborhood of those. Right, so your parameter estimates are in there somewhere. What's the worst you could do? So for small epsilon, if this is big for small epsilon, that means you have a really sensitive problem. Meaning you can be really close to the true parameter values, you're off by just epsilon, and you get a huge regret. There's a huge difference between your performance and the true optimal. On the other hand, if it was really small for big epsilon, that means there's a big flat region around the truth. As long as you're in there, you're going to do pretty well. Okay, so it somehow measures the difficulty of the problem. So if we assume A1 through A5 and those causal conditions, then for any delta and any A to t like before, diverges to infinity and its little O of t, the probability that v of pi opt minus v of the Thompson sampling estimator, the probability that exceeds delta, has this form. So there's a bunch of constants, k1 through k5, that the explicit form of these is in another paper. But it's exponential in t. So it's e to the minus kt. And then one of the constants, I put this explicit dependence on that radius up there to show that, of course, as it becomes more and more sensitive, the bound gets looser and looser. And you also see in the second part, this A to t showing up again. And if you stare at this long enough, you realize that, again, some part of it increases with A to t and some part of it decreases with A to t. And there's a sweet spot that minimizes this bound. And that's the same order as the minimizer on the previous slide. Okay, so again, you sort of see that there does seem to be at least a right order of magnitude as far as how much you should simulate. But you do get this sort of exponential concentration for Thompson sampling. Okay, so back to the regular scheduled program. When we're thinking about parametric estimation, in terms of just pros and cons, it's intuitive in the sense that you can say to a domain expert, we estimate the dynamics of the disease, and then we simulate a whole bunch to figure out what the right thing is to do based on those simulations. It allows you to leverage existing scientific theory in that you're looking at these dynamics models, and so there's a lot of work in disease ecology about the spread of white nose syndrome and other infectious diseases, and so you can bring those to bear in this problem. It's low variance because you've imposed all the structure. That means you can get it to go through even in very data impoverished settings. Early on, the MLE you might not be able to identify it, and you might have to be truly Bayesian early on before you go to the surrogate approach. You can extend it to non-stationary settings. Again, I mentioned using state space models or other kind of slowly evolving models. You can show that rate is optimal under what I would say are very strong conditions. Of course, the drawbacks, you put a lot of structure in the problem, and if that structure is wrong, you have bias. The computational is non-trivial, so you're climbing uphill in this space delta, which is a space of functions. So in general, that's not an easy problem. Anyone who's done stochastic programming knows that can be very difficult to tune and get right. And even if the delta you started with was interpretable, I mentioned this sort of linear combination of interpretable features, once you mix over it, you lose that interpretability. Yeah, so these are some of the, I think, the drawbacks there. I want to just show a few simulation experiments. So we'll look at spread of the disease across nodes in a network. The paper also has spread over a spatial domain. So we'll look at randomly selecting 1% of the nodes to infect at baseline. Then you do nothing for 6 time points, so it just spreads unchecked. And then after that, you're allowed to treat at most 6% of the nodes for time points t equals 7 up to 15. And the generative model is built from the white nose syndrome data. It's a variant of a gravity model. So for those who aren't familiar with the gravity model, it's basically that the probability of infection is linear on a logit scale. And the coefficients are going to be estimated using the white nose data and then rescaled so that if you didn't do anything for all 15 time points, you get 70% infection. And the reason to do that is just to make them somewhat comparable across different network topologies and network sizes. And then the initial state values are generated from a normal with mean 0 and identity covariance matrix. And the goal is to minimize the number of infected nodes at time t equals 15. So that's the goal. So those are the structures. We'll look at a grid. So I've just shown them in different sizes here. Scale-free and a 3 nearest neighbor graph. And as I mentioned, there are non-network structures that are also in the paper. In terms of competing allocation strategies, we'll look at doing nothing. So applying no treatment. All treatment, so that's sort of the gold unattainable standards. What if you just treat it everywhere? Myopic, which is to allocate treatment to the nodes with the highest predicted probability of infection. So that's an intuitive strategy. Just predict where it's going to go and treat there. Proximal, this is an ad hoc strategy where you try to identify a border. So that was done here in foot and mouth disease. So you try to identify some kind of ring or boundary around the disease and treat there to contain it. And then simulation optimization with that class of policies that I mentioned earlier on the talk, which is basically we construct a priority score at each location. We'll look at correct and incorrect dynamics model. So the correct one will be this time-dependent SI model, susceptible infected model. That was published in Nature in 2012, and the incorrect will be where the estimated dynamics depend only on distance. So the idea here was to try to severely misspecify the model. So it depends only on the distance to the nearest infected location. And as I said, the priority-based deterministic class with linear features. And those features come out of the estimated model. Okay, so here are the results. So the way this is set up is so the columns correspond to different network sizes, 100, 500, and 1,000, and the rows are different network topologies, so grid, scale-free, and 3 nearest neighbors. And then within each of those rows, we have the competing methods. So there's treat all, policy search, which is the proposed method, the proximal strategy, the myopic strategy, and do nothing. So by construction, the do nothing is about 0.7. Okay? And you can see that policy search was relatively close to treating everywhere, despite only being able to treat 6% of the nodes at each time point. In some cases, proximal did pretty well. In some cases, it did worse. Generally, it was better than the myopic strategy, although there might be some exceptions. So this is if the model is correctly specified. And the incorrectly specified model, you see things move a little bit. The policy search is a little bit worse now relative to treating everywhere, which is what you'd expect because it's using that model. You'll see that the proximal strategy doesn't change at all because it doesn't depend on the model at all. It's only on distance to the infection, and none remains the same. So it seemed to provide a benefit over maybe some more ad hoc strategies, at least in these simulations that we considered. And then to return to white nose, so we simulated the spread of white nose. Here it's sort of up to 2015, again, because that was sort of when we were working on, or when the first version of the paper submitted. There's an up-to-date, a slightly more up-to-date version that has data up to 2016, I think. But the results are qualitatively similar. And so here, there's 11,037 nodes. If you do nothing, you end up with about 43% infected. If you do the myopic strategy, you end up with 36. The proximal is 39. Simulation optimization was 22. So about half of doing nothing, and maybe 5 percentage points above treating everywhere. So it seems to give you a really large gain in terms of efficiency, or at least in terms of cost savings, if you thought about the cost of treating everywhere relative to just treating 6% of the nodes. And I should also mention that I didn't put standard errors up here, but they're sort of off in the third digit. Okay, so they don't affect sort of these numbers. Okay, so just to kind of wrap up, the idea of managing an epidemic, we pose as a spatial temporal allocation problem. An effective strategy has to somehow account for spillover effects. So in this paper, we did that through modeling. So we modeled the spillover effect. It's implicit in the models for those densities. Right? It has to be implementable online. Now, in white nose, you're making a decision once a year. So when you say online, it's not the same thing as guiding a missile, where you're making a decision every thousandth of a second or something. But the online component does mean that you have to incorporate all the data that's accumulated up till now and try to balance improving the model with doing the best thing given the model that you currently have. Computationally feasible, again, we have a year. And then you have to accommodate the evolving logistical constraints. So here we had one class pi, but if the constraints change, you could just change the class pi at the given time. So at any given time, you're assuming you're going to have that same class going into the future, but you could change it at any time. And if you knew how to forecast how that class would change, then of course you could do that too. We looked at parametric estimators. Of course, going to semi-parametric or non-parametric estimators is something to consider. I think one exciting part about all of this is that as data are accumulating, you have this opportunity to get more and more flexible with your model. So you really can think about sieves as being kind of a reasonable approach here, and not just maybe a theoretical construct. I hope I didn't insult anyone who works in sieves. Anyway, so there's a lot of open and exciting problems. I think this sort of imperfect measurement error, this imperfect measurement detection that we completely ignored here, right? We assume the states were perfectly observed at every time point, which is not true. And there's even reason to believe maybe that those measurements are correlated with whether or not the disease is there. Looking to scale to bigger networks, if you think about doing this in advertising, so we have some heuristics that can go up to, say, 10 million nodes or so, but they require a lot of sort of ad hoc computational approximations. I mentioned sieves already. Try to account for the stochasticity in the allocation in a way that really does optimize this trade-off between learning and optimizing given what you've already learned. And there's some evidence that the way we've done this, gives you a good rate. But in finite samples, you can certainly construct examples where you would have been better off doing more or less exploration. There are examples where you really don't have to explore at all, and you'll get good performance. And so that's something to think about, is how to improve the finite sample performance, maybe by tweaking Thompson sampling or doing something else. And another thing is, if you think about human diseases, the networks, you don't know them, and they evolve. And so trying to incorporate all of that into this framework. So one nice thing about taking a Bayesian point of view in this kind of problem is that you can put a distribution over the set of networks and the connections, and you can fold the whole thing into one big Thompson sampling estimator. Although the sort of details of how to do that, I think, are unclear. And so I think I will stop there. Thank you.
Thanks very much for the opportunity to propose the vote of thanks for this very interesting paper. I'm very glad to be part of this discussion. Rob asked me to stick to 10 minutes, so I'll keep an eye on the clock up on the wall. So essentially, we've heard very nicely the last 45 minutes about what is this paper about. So I'll just try to sort of very briefly summarize. So understanding the spread of infectious diseases is of great importance. Why? Because if we know how disease has been spread in the past, then hopefully that will prevent us from future diseases and outbreaks. Significant amount has been actually of effort has been devoted in developing models and methods for estimating parameters when we feed models to this data, and also try to make predictions in real time. However, to control the spread, we need to decide where and when to apply interventions. And in my view, there hasn't really been much work in this area, and I think this is a gap that this paper actually fills in, and in particular is concerned with developing a Bayesian framework to inform such decisions in real time, based on data. So my work is on sort of traditional, if you like, infectious disease modeling, and I've tried to talk about an alternative but still motivating application. It's something that I have been involved in the past with, and after reading the paper and being asked to discuss it, I thought, is there any ways such that I can take this methodology that has been developed and apply it to the problems I've looked in the past. So Eric said in the beginning that this white nose syndrome in bats is not very common in Europe, but it's very common in the US. In contrast, back in 2001, UK has experienced a devastating foot-and-mouth disease outbreak. And this is not really real data, it's some just made up data that I put together of farms in the UK where the red dots represent the infected farms. So suppose that there's currently an outbreak of foot and mouth. So DEFRA, so the Department of Environment, Food and Rural Affairs, would like some input as to how the disease spreads, as well as what sort of efficient control strategies we have and that can put in place. Okay? So essentially, let's say that we collaborate with DEFRA and we want to inform them as to future control strategies. So at any given time point during the course of the outbreak, what does DEFRA, or what do we know? So there will be some farms that are still susceptible, so they're not infected yet. There will be farms that DEFRA suspects that they may have been infected. There will be farms that they know for sure after some lab results that they have been infected. And also there will be farms that they have been infected, but we don't know about them. And as far as I understand, DEFRA would put in place several zones on confirmation of disease on the infected premises. So essentially, they've got different kinds of zones: protection, surveillance, and restricted zone, depending on whether or not they have suspected a foot-and-mouth disease in a particular farm. So they will restrict movement, or they will not allow sort of lorries to go to these farms, etc. So in the paper and the white nose syndrome application, Labour and co-authors assume that the infection status, the time since infection, as well as some other covariates are actually observed. And the model that describes the dynamics of the process is what is called the spatial gravity model, and has a GLM, kind of generalized linear model flavor, and is concerned essentially with modeling the probability of the disease spreading from location L to some location, or K to L at some time. So given the observed data up to time t, then the likelihood, the model can be fitted using either maximum likelihood or within a Bayesian approach. On the other hand, if we try to employ a more sort of traditional epidemics model, so for example an SIR model, either deterministic or stochastic, and let's stick to stochastic models for this discussion. So each individual will be either susceptible, or each farm will be either susceptible or infected or removed from the population. A key aspect in this kind of models is the rate at which new infections occur, and how long a farm, for example, or an individual remains infectious for. So one actually question I had, and I was trying to think how one can sort of, or how practical it is to adapt the proposed methodology in the paper if we were to consider a model of this kind, where essentially we have a rate of infection between a farm I and a farm J, rather than the GLM kind of model that has been used in the paper. Another aspect I would like to discuss is data on infectious diseases, highly dependent, and that has been highlighted by Eric earlier, but also they are incomplete, since the actual transmission process is not really observed. So we never sort of quite know when somebody or a farm has been infected. We observe the symptoms or some animal sort of dying, and that tells us something that, there has been, for example, a disease. So if the infection process was observed, or if we were to make some assumption about it, then fitting this kind of models to data is sort of relatively straightforward. It may be a bit expensive, but we can write down a likelihood and we can maximize it, or we can do Bayesian inference. In practice, however, we don't observe, as I said, the infection process, and to overcome this problem, there has been a lot of effort in developing methods to fit such models to data, mostly sort of simulation-based methods, so MCMC, ABC, and SMC. And again, I think it would be interesting to know if the proposed methodology or then the algorithm that comes with it will be feasible in practice for if we were to fit these models using, for example, MCMC, ABC, or SMC. Something that I read in the paper that I may actually have misunderstood, so this is like my disclaimer, that essentially in the paper it's proposed that the estimated treatment allocation is the maximizer over a pre-specified class of strategies over the mean outcome of a model. Now again, for me it was actually said alarm bells in the beginning. I thought, what is the mean outcome? But for example, if I simulate some data from an SIR model, a very simple SIR model, homogeneously mixing, and I look at the end how many people became infected, and I do this over and over again, then I get this sort of well-known bimodal behavior. So I've done this, I think, 10,000 times. About 4,000, the epidemic dies out very quickly, and in the other cases actually takes off. So how appropriate is to use the mean outcome of a model when, for example, the model is stochastic rather than a deterministic model or a GLM type? Are there any alternatives to it? And a few other aspects to finish off. Is there any way that contact tracing actually can be incorporated? What actually would that mean for the macro properties? So essentially, one of the things that people do from DEFRA is if they found foot and mouth in a particular farm, they will ask, okay, who did you have contact with, which are the farm, etc. So there's contact tracing. So can we incorporate that into the model somehow? How to deal with different models of varying complexity? Again, with these kind of problems, you start up maybe with a simple model, but then as you go along, you actually build this up, and you never quite know if the model is true. How can we actually deal with that in real time? And this is something actually that Eric also highlighted towards the end. There are actually computational challenges to address, especially if we are fitting sort of complex models based on partial observed data. And I would be interested to hear any more thoughts that the authors actually have. To conclude, the authors are to be congratulated for a very interesting paper that tackles an important problem, and I think it fills a gap in the literature. It opens up, I think, interesting avenues for further research, for example, how to incorporate these SIR type of models in developing control strategies. And however, I believe the computational challenges remain if sort of traditional epidemic models actually are employed. Therefore, I'm very glad to propose the vote of thanks.
Right, thank you very much to the organizers. It's nice to participate in a special occasion like this. And I've had a lot of fun reading and rereading this paper several times. I think it was probably on the second or third time through the paper that I was put in mind of the work of this man, Guglielmo Marconi. So he sort of famously brought together components, rather complex components from a number of different areas of science, and sort of put them together into a workable workable system of wireless telegraphy, and that really stopped people in their tracks. Like, wow! So here's some people saying, "Wow," wearing really cool hats. The analogy that I'm drawing is, I think this paper also combines a lot of quite complex pieces of machinery. Together with the author's own innovations, and really goes further than we could have done before. So it's quite impressive. The words at the top there are apparently the first wireless telegraph sent over water between Flatholm, just off the coast of Wales, and Penarth, just near Cardiff. So there's a local reference for you. But the other thing to highlight about this is, of course, Marconi's work was used on board, say, the Titanic, and was highlighted as a life-saving invention there. So I think here we're saving bat lives, and maybe down the road human lives as well. So it's really good. I couldn't resist just going back to the year I was born as well. So the RSS has discussed papers on similar topics in the past. This one dealt with the multi-armed bandit problem, and the seconder on that occasion was noting that this is a classic problem and a very hard problem. And he decided it was so hard that apparently sort of Allied scientists in the Second World War were just so occupied with this, they ironically considered dropping the problem over Germany as an exercise in intellectual sabotage. So I thought that was absolutely a lovely suggestion. The complexity of the problem is something that I want to talk about a little bit, sort of by way of some mathematical abstraction, just to draw attention to the difficulty of what's been achieved, but also hopefully simplify it a bit. So I apologize, I've used slightly different notation. I've used the notation of stochastic processes formally here, the most important component of which in this context is just this idea of information evolving over time. So that's the sort of the filtration script FT there, that we know more as time goes on. But there's basically two processes that are going on here. There's the X's, that's what we're doing, and then there's the Y's, and that's how nature reacts to what we're doing. And because the authors are being Bayesian here, we also have on this same probability space theta co-varying with the process X and the process Y. But I want to break down that probability measure P that describes the evolution of the whole system into the three components that the authors also use. Again, slightly different notation, but I'm using sigma here to denote a sort of strategy. So this is notation borrowed from Phil David and Vanessa Didalez's work, where it's basically describing how we are going to go from what we know at a particular point in time to our next decision. So these are a bunch of transition measures describing from time zero all the way to the end of time how we're going to decide what the next X is. So that could involve some randomness, or it could be deterministic. And then we have the second component, which is this model for how nature works. So that's my P theta here, and that's sort of how do we get our next Y, if you like. And then underneath all of this is some prior on theta. So just briefly to comment on that sigma, the strategy. I think I'm using this in a slightly more general sense than Eric did. I'm thinking of this as either at time zero, at baseline, or outside time if you prefer, but describing how we will react to each piece of information and whatever that information is. So that's a hugely complex thing. There's many possible options for that. But once we've fixed that, once we know how we will react, then we have completely characterized the probability measure under that strategy. So we know how things might turn out, the distribution of how things might turn out. And in particular, we can work out some means. So I think that this is sort of notionally what the authors are maximizing. So I've written the objective function from this paper just as f of y, but understand that as the discounted mean utility. It's some function of the whole stochastic process, again, going off to infinity. But I've indexed the expectation by sigma, because the idea is that this expectation depends strongly on our strategy. If our strategy is never do anything, then our expectation will be different to if our strategy is do everything at all time points or anything in between, or indeed in randomization. So it depends on that. I'm going to come back to the marginalizing over theta, because I think that's really interesting. This is a question about terminology. The paper sort of talks about estimating an optimal strategy, and I want to ask, is it maybe better to think, at least in these terms, as a computation? That it is basically an exercise in, here's the probability distribution, there's no data involved at this point, and we're basically saying, that's what the expectation is under this strategy. Here's another expectation under a different strategy. Which one's biggest? So is that a computation rather than an estimation problem? Of course, the implications will be estimation. Will depend on data, but the problem, solving the class of problems, is more a computation. So just coming back to that point about this objective, the paper and Eric in his presentation has described this balance between exploration and exploitation, and Thompson sampling sort of seems to achieve that. But I think it's interesting to look at this quantity and realize that there isn't any hint of that balance in it. This is basically just the mean utility. And it's precisely because this quantity has been marginalized over the uncertainty in theta that we might consider strategies sigma that involve some randomization. So that exploration-exploitation trade-off is sort of built in behind the scenes. So this, objective, complex though it is really quite a remarkable one, because we are asking sigma to design and carry out and implement the whole experiment and treatment. So if we can achieve this, I think this has a much wider implication than just the present context. But of course, that's very hard. And then I hope I've understood Thompson sampling right here. This is my characterization of it, and I found the sort of off-piste bit actually really helpful in Eric's presentation just now. But I think the idea is that at each time point we have a posterior, a sort of current posterior, if you like, theta given the current information, which we sample from, at least in principle, and then we find the best strategy sigma. And again, this will be a deterministic strategy if we assume that sampled theta is the true one. So that will be a deterministic one. We find the best one and do that at least for one stage. So my question, as I say, I think Eric's kind of addressed this, is in that calculation still, there is still a notion of what are we going to do at every point in the future. So this sigma is still a horribly complicated object, and so that computation of working that out, it wasn't entirely obvious to me what was being assumed about the future decisions in order to maximize at the Thompson sampling stage. And then the paper deals very reasonably with how we deal with evolving constraints, which I really liked. And I think it's sort of obvious that if there's constraints that are predictable in a certain way, I don't mean that their exact value is predictable, but their existence is predictable. So cost, for example. We might be able to anticipate that at every stage we have a limited number of dollars we're allowed to spend, and we can incorporate that all within the sort of information that's available to us, if you like. What was less obvious to me, and I'd be interested to hear the author's comment on, is whether we can incorporate, channeling my inner Rumsfeld here from my standing desk, the unknown unknowns, whether somehow we have treatments that are unanticipated at the start. But in order to decide that a treatment is optimal, do we have to model that those treatments could exist and that they might have properties that we can't even imagine? So it sort of comes back to where I started about, is the sample space, does that include also things that may happen that we just have no idea about? So that's a trickier one in my mind. So, as I say, I have really enjoyed reading this paper. This is a quote from Chesterton, which I liked. "Thanks to the highest form of thought and gratitude is happiness doubled by wonder." So I think that the authors of this paper have given us a huge amount to wonder at, and of course a little bit to wonder about, and it's with great happiness that I second the vote of thanks.
Thanks to the organizer for giving me the opportunity. So let me summarize my take on the paper. It's basically a spatiotemporal treatment allocation strategy using online reinforcement learning, and this extend the dynamic treatment regime DTR framework for personalized medicine into this new problem by incorporating spatial component into it. So I myself work in this dynamic treatment regime arena, and that's why I look through that lens and try to make some comments here. And this is applied to this emerging infectious disease setting, which is very widely appealing. Even though I said it's an extension from the DTR framework, here are some distinctions that I thought are worth mentioning. First of all, the interference between spatial locations, which Eric highlighted several times, the violation of the Sattva assumption. Then there is this curse of dimension or small n large p type phenomenon here, because there is scarcity of data at the beginning of the epidemic, and you still have to learn. And number of possible allocations is huge, so that's the high dimensionality. Next thing is, unlike the case of DTRs, here the independent replications of the data are not available. So that's like N of 1 trials in the clinical trial setting. Then there is this long time horizon with evolving logistical constraints. That means evolving classes of policy. That's an interesting feature that we do not see that much in the DTR. And then learning often happens online as opposed to the mostly offline and batch mode learning that happens in the clinical trials, smart sort of clinical trials in the dynamic treatments. So here are the main methodological innovations. First of all, the DTR literature is mostly dominated by frequentist ideas, even though there are some Bayesian works. Here it's mostly Bayesian, so this is a fresh perspective. So the policy search is done by approximate Thompson sampling, and so Eric and co-authors have really brought back Thompson sampling into statistics because it was almost forgotten. And then the other clever piece is that computation of the argmax of the value function without really computing the value for each and every policy within that class via stochastic approximation. So that I think is a cool piece, and that really manages the computation. I want to highlight a couple of things that might be missed, but I want to highlight. So even though the proposed policy search requires an underlying a working parametric model of the system's dynamics for the learning, that's not really the focus here. So the focus is only for optimal decisions. The focus is not to understand the disease dynamics. And this is where it differs from the mathematical modeling of infectious disease literature. So that's a different approach altogether. The other thing here is that, as the authors pointed out, one possible future research direction is to try to reduce the dependence on the working system dynamics model to develop more semi-parametric kind of approaches using estimating equations converted from the Bellman equation that comes in. That's the key feature of Markov decision processes. So I just want to point out that even in the batch mode offline learning setting in DTR that I have worked on, we have done something along those lines and gave us very good performance. So that's key for the Q learning where you share the decision rules over time point. So it has some similar flavor here. Okay, before I conclude, I want to ask a few questions. So the first one is about evolving system dynamics. So the main thing here, main feature in the paper is that the policy class changes over time, but the system is time homogeneous. But in many infectious disease contexts, the serotype of virus or bacteria causing the disease, it actually evolves. So, how do you tackle that kind of a problem? I heard Eric mentioning state space models, but I just want to, I'm a bit more curious that whether this is a matter of computational scalability or is it convergence of the algorithm that is affected, if that kind of a problem we have to handle using Thompson sampling and so on. So the other question, again, I think I didn't mention in the talk today, but in the paper, it says that it works under the completely observed states, and when there are partially observed states, then one can handle it by using sampling weights or imputation strategies in conjunction with Thompson sampling or policy search. But so is that the thing called partially observed Markov decision processes used by computer scientists, or is there something else going on in the computer science literature? And finally, so I understand that the optimal allocation is dependent on the class, but has there been any thought on optimizing more universally? For example, considering increasing sequence of policy classes and somehow taking a limit over all those classes to say something more globally, or does it make sense at all, or is it theoretically just too difficult to handle? So with those, I think I would conclude, and I really enjoyed reading the paper. Really want to congratulate. Thank you.
I thought this was highly original, impressively broad, and thoughtfully practical paper. And I'd like to make 2 points. One concerns the exploitation issue that's been mentioned a couple of times. One of the significant features of the paper is the balancing of online learning with practical application of treatments in real time. For an emerging epidemic, we just get one shot at learning what's going on and doing something about it. And I wondered if the authors have a view on whether a strategy like that should be taken back into standard optimal dynamic treatment problems. I'm thinking of personalised medicine, where we can assume ID individuals, and where, so far as I know, in the literature, there's always a sharp distinction between training data for modelling, estimation, determination of decision rules, and subsequent application of those decision rules. And maybe some blurring of that distinction might be beneficial. For example, suppose there are individual specific responses to treatment that are not captured by covariates or by the person's history, in other words, random effects. Then a Bayesian approach, as presented in this paper, in which we start by an assumption that the person is just drawn randomly from the population, and then gradually refine the posterior as we learn about the person and tailor the rules, not just the decisions, to that person, might be beneficial. Or, in the same theme, we can think about recognizing that point estimates from a training sample are just that, point estimates. They're subject to error. And perhaps we should continue to learn in practice through a stochastic treatment allocation strategy rather than a deterministic one, again as proposed in the paper. Of course, we then hit the ethical problem of whether we should apply the best possible treatment as known to date to the patient right in front of us, or think ahead to what's best for the group of people longer term. The second point I want to make is that there are conceptual similarities between the ideas and the problems considered in this paper and in optimal dynamic treatment problems generally, especially in relating to online learning combined with concurrent application, and what's called adaptive model predictive control that's developed in the engineering literature. Control engineers and people in optimal dynamic treatment work at times on very, very similar problems, but the methods are quite different. And I would suggest that more communication, or some communication even, between those two communities could be beneficial in both directions. I wonder if the authors have a view on that. I did enjoy the paper. I thought it was terrifically stimulating, and I add my thanks to the previous discussants.
So I get to read out the ones that have been sent in writing, since we have time to do that. So the first one is from Professor Peter Thal from the Department of Biostatistics at the University of Texas. Labour et al. Propose a dynamic strategy for allocating treatments to locations during an epidemic to limit spread of the disease in space over time by optimising a cumulative outcome, such as number of infected locations or total cost. It is edifying to see a prominent frequentist adopting a Bayesian approach for this challenging problem. Sequentially optimising functions of accumulated data allows existing dynamic treatment regime machinery to be applied to locations rather than to individuals, such as patients in a medical setting, except that spatial proximity may introduce interdependence between locations or interference. The methodology has several appealing features, including Thompson sampling to avoid getting stuck at a suboptimal strategy, and simulation to validate the methodology. For modelling, in my opinion, a Bayesian non-parametric approach should provide the most flexible and robust toolkit. My main comments pertain to application of the methodology to human epidemics, when number of deaths and financial cost both should be parts of any payoff function. As with application of any complex statistical method, numerous general structures must be made specific. The sets of locations and treatment strategies and data structure to be collected must be determined. Practicalities include the process of data recording, storage, quality control, acquisition, and computing the updated optimal allocation rule, all in real time. Ideally, this could be done via an internet-based graphical user interface. By magic, it's going to keep up with me. Well done. Since this and all other computer software must be tailored to the application, software development undoubtedly will be a non-trivial, time-consuming process. The methodology certainly will be required to pass political and administrative hurdles involving individuals from multiple regions, states, or countries, and these negotiations are likely to involve intensive discussions of payoffs and resource use. Since multiple decision makers with different utilities must reach a consensus, this in turn will affect key model components. Some combination of elicited expert opinion and historical data may be used to construct priors, and a prior to posterior sensitivity analysis will be useful to obtain consensus. This entire process must either 1. Precede the epidemic, which may be unrealistic, or 2. Be carried out at some time during a multi-year epidemic, as the authors note in section 4. I encourage the authors to think about these issues in the context of applying their methodology to mitigate recurrent annual global influenza epidemics, for which copious data are available. Otherwise, developing this useful methodology seems a bit batty. I shall carry on. So the next one comes from Marco Ferreira, who's at Virginia Tech. I congratulate Dr. Labour and his colleagues for their valuable contribution to the area of optimal spatiotemporal treatment allocation for controlling infectious diseases. I have two main concerns that are related to the objective of controlling an infectious disease epidemic, and I have a suggestion for possible future research. From the point of view of conservation of the species being affected, I think the main objective should be to ensure the long-term existence of the species. Consequently, my first concern is that I think the long-term existence should have a higher priority than the consistent estimation of an optimal control strategy. Thus, I think we will want to learn as fast as possible about how bad the disease may be, and then we would take action as fast as possible to ensure the long-term survival of the species. With that in mind, observational data, as opposed to stochastic allocation strategies, may provide biased estimates of parameters of disease dynamics, but may be good enough for making timely decisions on how to control the disease. An alternative way to look at this first concern would be that the amount of time needed to make a decision, including time for data collection, should be part of the total utility function. My second concern is related to the discounted total utility that depends on a discount parameter gamma, a member of 0, 1. This utility function discounts the future, and as such would weigh more heavily the near future than the longer-term existence of the species. The authors mention that their methodology can be extended to handle a cumulative utility function, such as the limit as t goes to infinity of the sum of u of y of t, which I think would be more in line with ensuring the long-term existence of the species. It would be helpful if the authors elaborate on how to accomplish such an extension. Finally, the problem of finding an optimal allocation strategy belongs to the class of optimal Bayesian design problems, and as such requires a maximization of a multidimensional integral. In light of this, a possible avenue for future research may be the extension of currently available stochastic algorithms that perform joint maximization and integration, such as the inhomogeneous Markov chain algorithm of Muller et al. 2004, and the inhomogeneous evolutionary MCMC of Ferreira and Sanyal 2014 and Ferreira 2015, to the context of optimal allocation strategies for controlling infectious diseases. The next one comes from Chengchun Shi, Rui Song, and Wenbin Liu from the Department of Statistics at North Carolina State University. We congratulate the authors for their very thoughtful article on online decision-making for infectious diseases. In addition to Thompson sampling, many other algorithms, such as the epsilon greedy algorithm of Sutton and Bartow 1998, and the upper confidence bound type algorithm of Agrawal 1995, can be applied to online decision-making as well. Taking the epsilon greedy algorithm as an example, at the J treatment stage, given the current parameter estimators beta j tilde and theta j tilde, and some naught less than epsilon j less than 1, we may set theta j as argmax over d, a member of d of ct of d, depending on beta j tilde and theta j tilde, with probability 1 minus epsilon j, and randomly sample theta j from D with probability epsilon j. It might be interesting to compare Thompson sampling with these algorithms. In step 6 of algorithm 1, the authors used policy search to compute pi hat j plus 1 by maximising the estimated value function among a class of treatment allocation strategies indexed by a finite dimensional vector. Policy search is a recent popular method for estimating the optimal treatment rule. We wonder whether classical reinforcement learning methods such as Q-learning could be used to estimate the optimal allocation strategy. From a practical perspective, it will be helpful if the authors could compare policy search with Q-learning under the setup of controlling emerging infectious diseases. Under assumptions 1 to 3, the authors show in equation 1 that the average discounted utility function under a given policy pi can be expressed by using the data generating model. We are curious if the authors can present more details on this equation. Why does it hold under the given assumptions? And in addition, is there a small mistake in it? The difference between these two expressions that sit on the wall behind me is that the first part of G of V is conditioned on yv minus 1 as well as hv minus 1 in the first one. So the question is, should there be conditioning on yv minus 1 in G of V? In algorithm 2, the authors use a stochastic approximation algorithm to approximate argmax over d of ct of d depending on beta and theta. And the algorithm relies on a sequence of non-negative step sizes, alpha j. And the authors comment that convergence guarantees require that the sum of the alpha j's is infinite. However, in the implementation, the authors use alpha j as Tor over rho plus j to the 1.25, and we notice that that is less than infinity summed over j for any Tor and rho bigger than 0. As a result, the algorithm may not converge under such choices of alpha j. Is it possible to use alpha j as Tor over rho plus j to improve the convergence of the algorithm? How am I doing? We have time. I shall keep going. The next one from Elizabeth Halloran and Michael Hudgins from the Department of Biostatistics in the University of Washington and Department of Biostatistics at the University of North Carolina. Labour and colleagues are to be congratulated for developing this fine framework for real-time data-driven decisions for managing emerging infectious diseases. Motivated by the white nose syndrome epidemic in bats, they developed methods for determining optimal online treatment allocation in space and time. The methods allow for interference, that is, treatment of a location can affect the potential outcomes in another location. Historically, interference can be placed in the context of what Sir Ronald Ross called dependent happenings. In his theory of happenings, Ross differentiated independent from dependent happenings. Dependent happenings are those in which the frequency depends on the number already affected. To this class belong infectious diseases, membership of societies, and sects with propagandas, trade unions, political parties, etc., due to propagation from within, that is, individual to individual. In Labour et al., the propagation of infection is transmission from one spatial location to another. Interference and spillover effects are governed by a gravity model describing the probability of spread of white nose syndrome between cave-bearing counties. A challenge is that the complexity of determining the optimal treatment allocation grows quite large with the number of locations, because the number of potential treatment allocations grows exponentially. The situation is similar when studying effects of vaccination of individuals in populations in the presence of interference. Labour et al. Use a clever combination of theory and computational methods to reduce the complexity by constructing a class of flexible strategies that are highly scalable. The cumulative expected utility at time t, for example, the proportion of locations infected at time t, is compared under different strategies, where their proposed optimal strategy slows spread better than two other rather rote strategies they call proximal and myopic. Intervention effects are defined within the gravity model, describing the local dynamics. Treatment can reduce the transmission probability both from a treated infected location through reduced infectiousness and to a treated uninfected location through reduced susceptibility. However, treatment does not cure an infected location, but only slows a process wherein every location becomes infected eventually, a depressing prospect for the bats. A simple extension would include that treatment could cure an infected site, allowing for elimination. We agree with the authors that one important avenue of future research will be developing methods robust to misspecification of the system dynamics model. For example, perhaps by using Bayesian model averaging over multiple system dynamics models. A final one that I have to read for you, which I don't think we have on the computer because it arrived rather late. So this one is from Dr. Daniel Lizotte at the University of Western Ontario. This work is an excellent example of applied statistics as the art of the possible. Starting from well-established formalisms of sequential decision-making, they develop practical methodology, and along the way they contribute to our understanding of how to bring these formalisms to practical application. Their work is also an important reminder, perhaps more salient to the computer science community than the statistics community, that not all important problems are big data problems, and not all small data problems have trivial solutions. I would like to discuss an additional application area that may benefit from this work. There is significant interest in health research on the topic of multimorbidity, defined as the presence of multiple chronic diseases in the same individual. Such diseases often share a complex web of causes, and their associated treatments often interact with each other as they shape an individual's future health. However, thinking about a joint treatment plan for several diseases simultaneously in many areas of medicine is still cutting edge, and often has little data-driven evidence to directly support its practice. The formalism developed by the authors, particularly the assumption of independent action control but dependent effects across units in the future, is well suited to this problem. At the same time, the multimorbidity treatment problem is qualitatively a bit different. We might think of different diseases as regions, each with a repertoire of actions that may be complex in and of itself. However, the number of diseases or regions would typically be small, fewer than 10, and the propagation of treatment effects across and among them could be very complex. This would require additional methodology to capture effectively. There are important art of the possible considerations in this domain that must be addressed as well. The output of any system for the multimorbidity treatment problem can only be decision support rather than decision making, which in part means that uncertainty over different courses of action must be exposed in a way that end users understand. This might be accomplished using the author's framework and somehow conveying the posterior distribution over optimal allocations. Furthermore, any recommended treatment may or may not be followed, an issue alluded to by the authors in their discussion of a compliance model. I'm interested to know the authors' opinions on their work's relevance to other such sequential decision-making problems with complex action spaces. Those are all the ones which we received in writing before the meeting.
First, thank you for the very thoughtful discussions. I have about 8 pages of notes, so I don't anticipate answering all of these here and now. I think some of these I'm going to have to think very carefully about, and I think I'm really grateful for those. And I did want to just, so what I tried to do was pick out some common threads and put them together, and maybe I'll speak a little bit about that, and then I look forward to trying to answer much more carefully the rest of the comments. So one that came up over and over again was a sort of practical application. So in terms of even the nuts and bolts of actually making software, but then also just a lot of the considerations in terms of cost, of the choice of utility function, and the choice of objective function. And I think that is an enormous problem. And the reality is that for these types of problems, our role as statisticians is to inform decision making, which means we need to take data and provide information that is useful to policymakers who are considering not only the objective function that we've used, however carefully we've constructed it, but then other factors like cost. There are certainly political factors at play here. If you want to talk about where to give resources through the DNR to the United States, you can't put them all in one, or it might be very difficult to put them all in one region, right? They care about what resources are allocated where. Certainly the issue of randomization, when we're talking about control of an infectious disease in humans, is something else that needs to be very carefully considered. And even communicating what's really going on. And so I think when talking about foot and mouth in particular, I think that drove home how important it is that you need to sell policymakers that whatever you're coming up with is grounded in science and is defensible from a scientific point of view. So a black box is not going to be enough. And so somehow taking the outputs of models like this or related kind of procedures and then somehow extracting some meaningful summary of how it's choosing to do what it's doing and why it's maybe outperforming another strategy is going to be critical. Another theme that came up was robustness. So that could be robustness to misspecification. It could be handling the fact that you have missing data and so on. And I think that's another important procedure. As Bibash mentioned, there are strategies through Q-learning. And I think in the connections to mathematical modeling and disease modeling, I think what's going to be useful tools when we combine them into doubly robust estimators. That if you have a mechanistic model that's correct, or you have an estimating equation that's correctly specified, if either one of those is correct, you get the right answer, and you get maybe some kind of efficiency gain if they're both right. I think that's something to think about. And I think there was a question about POM-DPs, and I think that's the right framework. But whether or not, what's the main obstacle? I think computation is going to be a real difficult thing there, because you're integrating over the state you didn't see given the information you do see. And so all this stuff has to then be folded into a giant integral over the state, the latent state. So in a POM-DP, you assume the thing you get to observe is not the actual state. The state you don't see, that's where the Markovian property holds. And so now everything becomes folded inside of a latent variable model, and so it becomes very, very difficult. I think some of the connections to a much more general mathematical framework I thought were really, really interesting, and I'm looking forward to sort of thinking about that when I'm not on the spot. And one other small thing I guess I should mention is that we had a very good AE who caught some of those errors. So the final version didn't have them, but they were right that there shouldn't be a Y in there. Let's see. Oh, and one other thing I think is interesting was raised the other alternatives for exploration. So epsilon greedy, UCB, or upper confidence bound sampling. And in this problem, when the dimension is so big, if you think about having 2 to the L actions, and you say, well, I want to choose the best action with probability 1 minus epsilon, and one of the other ones with probability epsilon, you have to put a uniform distribution over those 2 to the L options, and so it becomes very difficult to do that. So either you make epsilon so big that there's some mass on all those other options, or the chance of selecting one of the other options is epsilon over 2 to the L, so it's 0. And also you don't want to enumerate them all. So that was another thing that we were worried about. I think the UCB with the estimating equation might be a really promising approach. So that is, you're doing an estimating equation to get a Q function, and then you take that Q function, replace it with a upper confidence bound, and sample that way. I think that that may end up being an effective way to balance exploration and exploitation. So I look forward to addressing the rest of the questions. Again, I'm very grateful for these comments, and I think they're giving me a lot to think about. So, thanks.